today we're building with giants. Now, you might not see them, but they are literally everywhere. In the water bottle in your hand, the jacket you're wearing, even the parts in your car. We're talking about polymers. But how do these massive molecules actually work? Well, let's find out. We're going to build one from the ground up, single link by single link. All right, here's our game plan for today. We're going to start with the absolute basics. What are these things? Then we'll look at the chemical glue that holds it all together. After that, we'll see how the chains are actually constructed, how their 3D design changes absolutely everything, and finally, we'll connect all that deep-level chemistry to the materials we use every single day. So, first things first, before we can build anything, we have to know what our building blocks are. Let's get right to the core of it. It all starts right here with the monomer. I mean, the name gives it away. Mono means one part. This is our individual Lego brick, our single paper clip. It's the fundamental piece we're going to be connecting over and over and over again. And when you link all those monomers together, what do you get? A polymer. Poly, of course, means many parts. It's this process of creating incredibly long chains that gives materials like plastics their amazing and sometimes surprising properties, their strength, their flexibility, all of it. Okay, and this is where it gets really interesting, because how those chains are arranged completely changes how the material behaves. On one hand, you've got thermoplastics. Think of a big bowl of spaghetti. When you heat it up, the chains can just slide past each other, which means you can melt it down and reshape it. But on the other hand, you have thermosets. These are much more like a fishing net. The chains are all chemically locked together in a rigid grid. Once you set that shape, that's it. It's permanent. So we have these massive structures, right? Whether they're like slidable spaghetti strands or a rigid net. But what's actually holding them together? Well, you need some seriously powerful chemical glue. Let's take a look at the bonds that tie these all together. Now, there are a few types of primary bonds, but for polymers, there's one undisputed champion, and that's the covalent bond. This is where atoms actually share electrons, forming an incredibly strong and stable link. You can think of it like a firm chemical handshake. It's this powerful connection that creates the tough backbone of almost every polymer chain out there. But here's the thing, and this is so important. It's not just about the bonds in the main chain. The forces between the chains play a huge role too. These secondary forces, like the hydrogen bonds you see in nylons, act like tiny molecular magnets pulling the chains together. They influence pretty much everything, from the polymer's melting point and its stiffness to whether or not it'll dissolve. Okay, so we've got our building blocks, the monomers. We've got our glue, the chemical bonds. So how do we actually assemble the whole thing? This is where we get into the really cool process of polymerization. One of the main ways to do this is called chain polymerization, and you can honestly think of it like tipping over a huge line of dominoes. It all starts with initiation, a chemical spark that creates an active spot. Then comes propagation, where monomers just start adding on, one after another at lightning speed, whoosh! And finally, termination, where the reaction is stopped and bam, you got your finished polymer chain. Now, if chain polymerization is that super fast domino rally, then step polymerization is a little more, well, gradual. It's more like building with Legos, one piece at a time. Here, different molecules react with each other, step by step, to form a link. And a lot of the time, with each new link that forms, a tiny molecule, usually water, gets kicked out. Okay, so we've built a chain. But here's where we go from simply building to actually designing. See, the way the individual atoms are arranged in 3D space, the polymer's architecture, that is what truly defines its final properties. It's not just what it's made of, it's how it's all put together. And this example just illustrates it perfectly. Natural rubber and this stuff called gutta percha are made of the exact same monomer. But in natural rubber, the chain has a cis configuration, which gives it that bouncy elastic feel. In gutta percha, it has a trans configuration, making it rigid and leathery. Same atoms, same ingredients, just a tiny flip in the arrangement, and you get two totally different materials. It's incredible. This idea of architecture also gets into something called tacticity. First up is isotactic. This is where all the little side groups hanging off the main chain are lined up neatly on the very same side. It's a perfect, orderly stack. This regularity lets the chains pack together super tightly, which creates strong, crystalline materials. Next, you've got syndiotactic, Here, the side groups are still in a nice regular pattern, but now they alternate perfectly from one side of the chain to the other, back and forth, back and forth. This orderliness also lets the chains pack together really well, making for some strong materials. And finally, there's atactic, and this is just pure chaos. The side groups are arranged completely at random, all over the place. This structural mess means the chains can't pack neatly at all, so they end up in this jumbled, amorphous tangle. And that is why atactic polystyrene, like you'd find in a clear disposable cup, is transparent and kind of brittle. Controlling this structure is really the key to modern material science. All right, we've designed our monomer, we've chosen our bonds, we picked a polymerization method, and we controlled the 3D architecture. So, now for the payoff. How does all this fundamental chemistry actually turn into the materials we use every single day? Believe it or not, this story doesn't even end once the chain is made. We can actually perform more reactions on the finished polymer to tweak its properties. The most famous example, of course, is vulcanization. Back in the day, innovators like Hancock and Goodyear figured out that if you heat natural rubber with sulfur, you create these cross-links between the chains. And that one step transformed a sticky, almost useless goo into the durable elastic rubber we all know today. A total game changer. And just look at the unbelievable scale we're talking about here. These are not lab curiosities. These are foundational pillars of our global economy. Even back in 1997, you can see the US and Western Europe were using millions upon millions of tons of these materials. Polyethylene for packaging film, PVC for pipes and siding, these materials literally build our modern world. So we've gone on this entire journey from a single monomer all the way up to these massive materials that shape our world. We've seen that the age of just stumbling upon new general-purpose plastics is, well, it's mostly over. The future is all about designing highly specialized, special-purpose polymers from the ground up. And that leaves us with a really fascinating question. As our ability to engineer things at the molecular level gets more and more precise, what incredible problems will the next generation of custom-designed polymers solve?